Okay, dear all, today let us go for second session. Let us continue with the time response analysis. We are going to discuss standard test signals. So, in control system, we apply some standard test signals to predict the performance of the system. In many practical systems, the actual input signal is not known to predict the output of the system. At the time of designing of a system, so we should know what is the proper input, but it is not possible in many practical systems to know the actual input. Therefore, we take the characteristics of the input signals and those characteristics, which signals those characteristics will resemble. Those signals will be taken as the input for the system to predict the performance of the system. Now, what are the characteristics of an input signal? That is sudden shock, sudden change, so constant velocity and constant acceleration. These are the characteristics of input signal. So here, this impulse signal is nothing but sudden shock. Sudden shock means suddenly the signal rises. So impulse signal imitates sudden shock. A step signal imitates sudden change. A ramp signal constant velocity, similar to constant velocity. A parabolic signal imitates constant acceleration. Hence, these signals are considered as standard test signals in our control system. Hence, we should know the behavior of those signals with respect to time, because we are doing time response analysis. Hence, let us discuss one by one in detail. Now, let us discuss the first signal, that is impulse signal. What is an impulse signal? An impulse signal has infinite amplitude. It has an infinite amplitude at t equal to 0 and 0 amplitude for t less than 0 and for t greater than 0. So, this impulse signal can also be represented by a short duration pulse. Here you can observe width is epsilon, height is 1 by epsilon, and these are the limits. Now, suppose if I make epsilon tends to 0, if I make epsilon tends to 0 here, what happens? This width decreases and it becomes it reaches the origin. At the same time, if I make epsilon tends to 0, 1 by 0, so this will increase. It moves towards infinity. That's why, so this is same as this one. So this is actually how it is represented. But as per our definition, so an impulse signal is a signal which has infinite amplitude at t equal to 0 and 0 amplitude for t not equal to 0. Therefore, I can write here mathematically delta t is equal to limit epsilon tends to 0, limit epsilon tends to 0. I am writing what is delta t value. So, limit epsilon tends to 0 r of t. What happens now? Delta t value is equal to, so if I make epsilon tends to 0, for this value r of t becomes infinity for t equal to 0. So, if I make epsilon tends to 0 in this, then what happens? So, this value of r of t reaches infinity. Delta t value becomes infinity for t equal to 0. And its value is equal to 0 for t not equal to 0. This is how a impulse function can be represented mathematically. Okay? Okay. So, area of impulse signal. So, area of the impulse signal is equal to integral minus infinity to plus infinity. So delta t dt. So now here, what is delta t? Here area. So width into height. That is 1 by epsilon multiplied by epsilon. 1 by epsilon. So this is r of t. You can see here, this is r of t. So that is equal to 1. That is, area of the impulse signal is always equal to 1. Area of the impulse signal is always 1. This is also called as weight of impulse signal. Weight of impulse signal. Okay? In time domain analysis, this can be represented as delta t value is equal to 1 for t equal to 0. Delta t value is equal to 1 for t equal to 0, and its value is equal to 0 for t not equal to 0. This is in time domain. So in frequency domain, that is nothing but in S domain. In S domain, to get it this, you have to take the Laplace transformation. So Laplace transformation of delta t is equal to 1. That is, Laplace transformation of delta t is equal to 1, which represents that. So if you apply an impulse signal, unit impulse signal, the input r of x will be considered as 1. So this represents, if you apply a unit impulse signal to a system, then the input value r of x will be considered as 1 for this signal. Now let us discuss the remaining signals. A step signal is a signal whose amplitude or the level or the value changes from one level to the other level in 0 time. That means at t equal to 0, its value changes from one level to other level. Let the value or the amplitude be a. Therefore, mathematically this can be represented as, if I take this is as r of t, then r of t value is equal to what? A. For what? For t equal to or greater than 0. Equal to or greater than 0, its value is a, and r of t value is equal to 0 for t less than 0. Less than 0, its value is 0. This is how it can be represented mathematically. Now, always we consider unit step input. So for unit step input, the amplitude will be considered as 1. When amplitude is 1, then r of t is equal to 1. R of t is equal to 1 for t greater than or equal to 0. Now we want the input in frequency domain. It is in time domain. To get in frequency domain, we need to take the Laplace transformation. So taking Laplace transform, then r of t becomes r of s, and Laplace transformation of 1 is 1 by s. And what this represents, if we are applying unit step signal for a system, then we take the input value r of s as 1 by s. Hence r of s equal to 1 by s for unit step signal. Okay. Now let us go for the next signal, that is ramp signal. Let us define what is ramp signal. A ramp signal is a signal whose amplitude changes linearly with respect to time. Okay. So linear variation with respect to time. Such a signal is called a ramp signal. So here the slope is taken as a. So mathematically this is represented as, this signal can be represented as r of t is equal to, slope is taken as a, and it is changing with respect to time. So R of t is equal to AT for t equal to or greater than 0 and its value is equal to 0 for t less than 0. Okay. Now again, as usual, let us consider the slope as 1 considering unit ramp signal. So for unit ramp signal, what is slope? Slope A is considered as 1. Therefore, this R of t becomes t because A is 1 for t greater than or equal to 0. Now let us express this in frequency domain. So to then taking Laplace transform of a point, then R of t becomes R of s is equal to Laplace transformation of t to the power of n is equal to n factorial divided by s to the power of n plus 1. So since n is equal to 1 here, 1 divided by s square. So 1 by s square. So what is this represents? If you consider a unit ramp signal for a system, then the input value, that is R of s, will be considered as 1 by s square. That is R of s equal to 1 by s square for unit ramp signal. That's all. Now let us take the next signal. So fourth signal is parabolic signal. What is a parabolic signal? A parabolic signal is a signal whose amplitude is proportional to square of the time. Square of the time. It is represented like this. So its amplitude is proportional to square of the time. Now if I take the amplitude as A by 2 instead of A, so to get the similarity between the previous signal and this signal, we are going to consider the amplitude as A by 2. Later you will understand why I have taken A by 2. So now mathematically again this can be represented as R of t is equal to what? A by 2 is the amplitude. It is proportional to square of the time, hence it is t square. So mathematically a parabolic signal is represented as A by 2 into t square for what? For t greater than or equal to 0. So greater than or equal to 0, its value is this. And for t less than 0, its value is 0 for t less than 0. So this is how it can be represented mathematically. Now again, if I consider unit parabolic for unit parabolic signal, what is amplitude A is equal to 1. And what happens? This R of t value is equal to A is 1, that is 1 by 2 into t square. Holds good for t greater than or equal to 0. Now it is in time domain. Let us express in frequency domain, taking Laplace transformation. Taking Laplace transform, and R of s is equal to, so 1 by 2 Laplace transformation of t square. So you know that Laplace transformation of t to the power of n is equal to n factorial divided by s to the power of n plus 1. Here n is equal to what? 2. Therefore this can be written as 2 factorial divided by s 2 plus 1, that is 3. So 2 factorial is 2, so 2 to cancel, you get here 1 by s cube. That is what the conclusion. So R of s value is equal to 1 by s cube for unit parabolic input, parabolic signal. Now let us conclude all the 4 signals. So conclusion from this discussion, we have considered 4 test signals. We have considered 4 test signals. First one is unit impulse signal, then unit step signal, unit ramp, unit parabolic. So for this, R of S value is 1, step 1 by S, ramp 1 by S square, and parabolic 1 by S cube. That means you can see the similarity of these four signals. That's why when I was discussing about parabolic, I have taken the amplitude as A by 2 so that A is not coming into picture and 2 get cancelled there, so you got 1 by S cube here. So this is how easily you can remember the relation between one signal and the other signal, and these signals are applied or considered to predict the output of the system. So hence this information is very important to discuss the further sessions. Thank you for watching.